Okay. Thank you so much that even during these special times we're able to kind of present our work and get into contact. So I've prepared a very short intro, and I'm going to keep it very short because we're quite we have a schedule today. So welcome to the symposium. Unpacking the association between spatial and mathematical thinking. We are going to look forward to 4 presentations in which we will hear something about investigations about directional and causal effects. And I've organized the symposium together with someone you may well know, Andrew Ribner. And this is the overview of what we are going to expect today. We have 4 presentations. The first one from Yunfeng He from the University of Tübingen. The second one from Ilyse Resnick from Canberra. How late is it now in Canberra?
It's 11 o'clock at night.
Okay, you're brave.
Okay,
good. All right, so then we will have a presentation from Katie Gilligan from the University of Surrey, and finally from Tobias Kahl from the University of Basel. So I will keep it very short just because I won't, take some time from you guys. And yeah, please join me in welcoming Yunfeng He. Where are you? Feel free to share your screen. Wait, where are you? Ah, there. Yeah.
Could you please see my screen now? Thank you.
Yes, yes.
I'm Yunfeng He. Very happy and honored to participate in this symposium. And I'd love to share with us the topic on directional association, numerical associations in gifted children. Lots of evidence shows that there is a bidirectional links between the number processing and the space. One of the most studied is the SNARC effect, which is the spatial numerical association of response codes. As is shown in this picture, when the participants are asked to judge whether the number on the screen is odd or even, or whether this number on the screen is bigger than 5 or smaller than 5. He is asked to respond with his left hand or right hand. And then if we focus on his reaction time, we will get a straight line with a negative slope, such as in this picture, the x coordinate is the digit and the y coordinate is the DRT. I show how to calculate the DRT, and this straight line tell us responses to the relatively small magnitude numbers are faster on the left-hand side, and the responses to the relatively large magnitude numbers are faster on the right-hand side. And this effect is the SNARC effect. The SNARC effect is prevalent across all the lifetime, and it observed in about 70 to 80% of individuals. Then question naturally arises, that is, which variables correlate with the SNARC effect? There is some correlates has already reported in the previous literatures. For example, reaction time characteristics. It showed slower and more variable responses, longer mean RT and larger intra-individual variability in RT, or standardized deviation in RT linked to a stronger SNARC effect. And on the other side, what is the relationship of the SNARC effect and the mass skew is still unknown. There is some mixed result. Second, from our new paper, elementary spatial mapping of numbers might be related to arithmetic ability. But until now, we didn't know how and what is the relationship between the SNARC effect and the mass skew. And then let's take a look at all the studies focused on the relationship between the SNARC effect and the mass skew. We divided into all the results into 3 categories according to the mass skew level. I think you can see it's low mass skew level and the normal mass skew level and the high mass skew level. And we also decided into 2 categories according to the participants' age. It's child study and adult study. And every results, after every result, there is a sign, a plus sign or minus sign or nothing. Plus sign means positive correlation, and minus sign means negative correlation. Nothing means there's no results. There's no correlation between the SNARC effect and the mass skew in this study. And we can see it's like that pattern. All child studies, the pattern is positive correlation or nothing. And in the adult studies, it's like negative correlation or nothing. And one point is the correlation between the SNARC effect and the mass skew is still missing in the children with high mass skew level. And obviously, we didn't have a mathematician in children, as Dr. Chipra report in 2016. But we did have some intellectually gifted children, who generally are excel in mass skew and get more mass training compared to their normal peers. So, if we focus on the gifted children, we can tell it's the relationship between the SNARC effect and the mass skew is linear or non-linear. And besides, testing gifted children are free from some confounding factors such as reaction time. As I reported before, reaction time correlated with the SNARC effect, and children with low mass skew sometimes generally have a longer reaction time, which would mix the result. Then that is why we decided to test gifted children and their SNARC effect and its relationship with mass skew. And maybe somebody will be curious about how we get the gifted children, and this is the main procedure. And at last, we get 74 gifted children and 91 normal children. And we use the Raven standardized progressive metric to double check their intelligence, and we use parity judgment to test the SNARC effect. And we use the arithmetic fluency to test their mass skew. According to the previous literatures, we use 2-digit by 1-digit multiplication as our task. About the group comparisons, we conduct 3 analyses. One is main analysis based on the Chinese selection process. And the second is intelligence-based analysis according to their performance on RSPM. And the third is arithmetic performances-based analysis according to their performance on their arithmetic fluency task. And this is the descriptive information of all our participants, because from the main analysis, we got that many children, and about this intelligence-based analysis, we got this kind of children, and the last we got these children, and you can also see their grade and their age. And we found gifted children are faster in parity judgment. You can see from here in the reaction time, and they have smaller intra-individual variability, and the gifted children also achieved better on arithmetic performance and intelligence. And from the correlation metrics, we also can find the SNARC effect is not related to math skills nor intelligence. And from this table, first we can see the control, the control group, we replicate the SNARC effect. This is what we expected. And importantly, we also see in gifted children, they also have a robust SNARC effect. And when we compare the differences between the 2 groups, Franken test and bias analysis also show us there's no differences between the 2 groups on the SNARC effect. And this is the main analysis. When we double check it on the arithmetic performances basis analysis and the intelligence basis analysis, the results is the same, which is there's no differences between the 2 groups. And then we fill the gap in here and find the directional spatial numerical associations in gifted children with high level math skills didn't differ from the controls. And leading by the Dr. Chipra, we proposed a model to explain the postulated mechanism affecting the observed SNARC effect. If you, because the time limited, you can find more information in this paper. And the conclusion in our paper is this is the first time we examine the SNARC effect and its relationship with arithmetic skill in gifted children, and we replicated the SNARC effect in gifted children, and the SNARC effect didn't correlate with intelligence nor math skills in our sample. And the most important finding is there's no significant differences in the SNARC effect between gifted children and the controls. And I would love to thank to my collaborators and thanks for your attention.
Thank you very much, Yunfeng He. You're perfectly on time. Thanks a lot. And yeah, we're looking forward to questions. Are there any questions? You can either just ask, or you can let me know in the chat, whatever you prefer. There is one in the chat from Moitaba Sultan Lu. So both Cohen's D and BF suggest non-conclusive SNARC in gifted, right? Maybe you can share this particular slide.
Okay. Oh, sorry. If I understand correctly, Mushtaba want me to share this screen, this page.
Does that answer your question?
Thanks for the presentation. Yes, I had them in mind, but I was just wondering whether we can really conclude from Cohen's D point 27 and base factor or null hypothesis of 0.6, whether we can conclude that whether or not gifted children show SNARC effect or not.
Do you mean the quantity, the value is not quite big?
Exactly, so, exactly. And also base factor is like in the range of being conclusive.
Yeah, we discussed some limitation in the discussion, but because we take three comparisons based on three different groups, and the result remain the same. So at last we conclude.
Yeah. So comparing to adults study that Christoph did in mathematician, can we conclude something here? I don't know, maybe Christoph can also join the discussion.
Yeah, so basically in mathematician's paper, it was like at the time when we could not calculate the one sample, like the one sample t-test, because like JASP was not around at the time. Like the effects are maybe not super spectacular there, but they seem to go into the same direction, and still like the effect was there. It was maybe not super spectacular, but also even though we had relatively large samples, the comparison was also non-significant and rather supporting the null.
Right.
Although not super strong, as you could see from bias factors. So.
Okay, thank you.
There is one more question from Martin Fischer now, and I suggest that this should be the last one so that we can go on. Do the gifted children excel in abacus soroban, or are they less good because they can do it mentally?
Excel in...
So I'm not sure whether in this group, as I remember discussions on this paper, whether they were particularly trained on abacus, or were they, Yunfeng?
No, they are not specific. They didn't get a specific training about abacus. They do it mentally or not? We didn't check in this study.
Yeah, but it's
their age. It's from the third grade to 5th grade. I think it's very hard for a child in that age can do the 2-digit by 1-digit multiplication in mentally. Just
yeah, but the question was rather whether they are trained to do the things with abacus or not.
No. Yeah.
All right, then I would say, I'm sorry, we don't have the time for another question. I'm going to be very strict today. But there will be, of course, time for email and, bilateral communication between between you guys. So please correspond afterwards, and I'm going to lead us to, or guide us to the next presentation, which is going to be from Ilyse. So let's get
All right,
started.
so I have to share my screen here. Let's see. And can you see anything?
Yes.
What do you see? Do you see my presentation?
Yep.
Yep.
Yep. Okay, good. Woohoo. All right. So hi, everybody. Just get my mouse back on the right screen here. Thank you for having me. My talk is going to explore why there's growing evidence that fraction number line estimation is strongly predictive of mathematics achievement. And I'm going to suggest a role of spatial scaling, which is the ability to imagine relations growing or shrinking proportionally. So to do this, let's start with an example of what fraction number line estimation is. So you would see a number line like this going from 0 to 1, or it could be 0 to 5, and you would have to say where a given fraction, so 3/7 here, would be located on the line. And for those of you playing at home, here is the correct answer. And as I mentioned, fraction number line estimation strongly predicts later mathematics achievement. Unfortunately, most of this research has taken place in the United States. Now, there is a few exceptions, one of which Tobias et al. Examined China, Belgium, and the United States. And arguably, these countries are very different on a number of factors. And so the aim of the current study is to examine the relation between fraction number line estimation and mathematics achievement in two countries that are more similar. And so in this case, Australia and the United States. And the table here just shows a number of ways mathematics education is similar and cultural contexts are similar across Australia and the US. However, there is one key difference in Australian mathematics education is that they highlight measurement models when teaching fractions, whereas United States highlight part whole. And this difference is what's going to help us explore the role of spatial scaling. So what I mean by measurement versus part whole, so there on the left, you have measurement model, which includes continuous representations of fractions like number lines or rulers. You're going to measure, how long something is to the fraction. Whereas part whole models are going to be area models where you have like one piece of the pie shaded in, or discrete models where you have a number of sets within an objects within a set. And more recently, the Common Core in the United States have included a measurement model, but nevertheless, teachers and textbooks don't typically include this representation, and instead they're focusing in on that part whole representation. So the current study had students with similar demographics from Australia and the United States. They completed a 0 to 1 number line and a 0 to 5 number line estimation task. And we had two groups in 4th grade and 6th grade. And this is just because this is when students receive their bulk of fraction instruction in both countries. And there's just a lot of information on this slide. My approach to timing was to throw a lot of stuff on and then just tell you what the take home is. So the takeaway here is that Australia is outperforming the United States on fraction number line estimation. And so this is going to support this measurement model approach. The students are more accurate. So the numbers in those cells is percent absolute error. So the larger that number is, the worse that they're doing. And the US it has more error than Australia on this task. This table is going to summarize the relation between number line estimation and mathematics achievement. So they took the RAT standardized mathematics assessment, mostly calculation, addition, subtraction. There are fraction items on this, but none of the students got to it. They are at the very end. And so what we can see here, what do I have up? We can see in the, for the United States, that the 0 to 1, 0 to 5, and if you take a composite score of both, they're all related to mathematics achievement. So I have correlations here, but also in predictive models, they are predicting mathematics achievement. And this is aligned with all this previous work, highlighting the role of magnitude in supporting math's understanding. But when you look at Australia, you can see that the 0 to 5 number line for 4th graders is not related to mathematics achievement, and the 0 to 1 isn't predictive of 6th graders' mathematic achievement. For 6th graders, it's likely due to low variability. The 6th graders were just really good on this, but I'm going to propose that perhaps on these tasks in this sample in Australia, these students are not actually engaging in that spatial representation of magnitude, spatial scaling. Instead, they're using some other strategy, and that's why the number line estimation isn't predicting mathematics achievement. So to do this, I'm going to begin by introducing a proportional reasoning task. And so in this task, we have Goldilocks there in the corner. She likes her chocolate milk a certain way. And that's on the left. And the student is asked to identify which chocolate milk combination is going to be the same on the right. In this case, the example I'm showing you is a continuous proportion, which tends to elicit that spatial scaling strategy. So the child's going to, there's no strategy given. They're just likely to use their imagination to imagine that proportion growing or shrinking to see which one's correct. But the same task can be presented as, I'll call Vigoli et al. Say discretized or truly discrete, which tend to promote more error-prone and less efficient counting or matching strategies, where they start counting the individual blocks that are demarcated. And then we can conceptualize these different proportional reasoning tasks as aligned with the fraction tasks the representations I've already presented. So you have the continuous, the area, and the discrete. And so given this relation, the current study wanted to examine if the emphasis on measurement models lead to better proportional reasoning then in tasks that elicit spatial scaling versus counting strategies. Are those Australian students going to do better because of their measurement model training? And then, of course, mapping this onto the relation between fraction number line estimation and mathematics achievement. So again, a lot on the screen. The first thing that I want to point out to you is the discretized and discrete column. So the middle column and the far right column. Australia is significantly better than the United States on the discrete and discretized, suggesting that a curriculum focusing on measurement models helps complete these proportional reasoning tasks. However, if you look on the left on the continuous model, there's no difference between Australia in blue and the United States in orange. So I should, direct everyone to that kind of stuff. There's no difference. And recall that the continuous representation in these proportional reasoning tasks is going to likely promote a spatial scaling strategy. And so this could, taken together, this could suggest that it's not that Australian students are better at proportional reasoning. It's not that that proportional reasoning skill has improved because they're the same on the continuous ones, but instead it's just recognizing when to implement the spatial scaling strategy. So, and in this case, yeah, so specific tasks and training, so the continuous task or the training using the measurement model are promoting these spatial scaling strategies themselves. And so recall, this is the table I showed you before between the relation between number line estimation and mathematics achievement. And here I'm just going to map on the relation with proportional reasoning. And starting with the US, we see that proportional reasoning correlates in all instances. But for Australia, proportional reasoning is only correlated when fraction number line estimation is predicting mathematics achievement. So when there's not that significant connection there between number line estimation and mathematics achievement, you also don't see it with proportional reasoning. And again, I mentioned before, those 6th graders are probably pretty good. There's probably pretty low variability on the 0 to 1 number line for them. But for the 4th graders, as I said before, perhaps they're not using a spatial representation for 0 to 5. They're pretty inaccurate, and previous work shows that students use inefficient heuristics or rule-based reasoning to try and complete fraction magnitude tasks if spatial scaling strategies aren't available, or if they're just choosing not to use them, I guess. And so in this case, perhaps the students are not engaging in spatial scaling strategies to complete the fraction number line estimation task, and in turn, it's not predictive of mathematics achievement. And so then a key part of how fraction number line estimation supports mathematical achievement is through the development of an accurate spatial representation of magnitude that can be flexibly and proportionally scaled. And this interpretation is aligned with work by Liz Gunderson that shows the number line mediates the relation between spatial skill and mathematics achievement. And so just a very quick summary, we see that Australia is, let's see, fraction number line estimation predicts mathematical achievement across country, and this is going to be aligned with the integrated theory of numerical development, which I didn't explain at all, but just kind of this more, universal learning of number theory. But the measurement model is more effective than an area model for teaching reasoning about fraction magnitude. But I would note that teaching the number line without any kind of spatial strategy may lead to using heuristics. So the US doesn't teach it at all, and you see that it's predictive because maybe those students are, they're either using it so they're pretty good at it, or they're not. But in Australia, where they're teaching the number line, the students might be also memorizing locations or developing other kinds of heuristics that help them out. And then they're subsequently not estimating on these novel number lines they're not as familiar with. There's a relation between fraction magnitude and proportional reasoning, and that these certain tasks are eliciting visualization strategies versus counting or matching strategies. But it's probably not, my interpretation is that it's not improving the actual proportional reasoning skill, it's just when to implement that. And so finally, I think I'm on 11 minutes. Wenke let me go 1 minute over. Thank you to my collaborators on this and all the participating schools. And are there any questions?
Thank you very much, Ilyse. No problem at all. So let's go into the discussion. So are there any questions?
Yep. Yes.
Go ahead. Yes. Yes.
So like very nice talk, and then just like I have quite often this problem, so to say, with the number line estimation task, that like the question is whether we are like really measuring or predicting like understanding of whatever number line, whatever it is, as a predictive to like more complex math operations, or it's just that it's actually kind of good understanding on math allows you in the first place just to do the task.
Yeah, and I guess I'm just trying to think of, there's another paper, for some reason I can't think, I think Nicole Hansen is the first author on it, along with Nancy Jordan's group, using a cross-legged panel model that shows bidirectional relation between the two, but that a stronger, more consistent relation with fraction number line supporting mathematics achievement compared to the other way around.
Mm-hmm.
So I don't know if so that would be a paper that might be
like
so that's
can be, but also like the fraction one. The fraction one is also like a more difficult than the regular one, probably, because you have like the decimals which you need to understand, and they are like less intuitive than the whole numbers, right?
Yeah, so I'm not sure, so I understand your question. So there's different kinds of magnitude estimation you could do, whole number, decimal, or fraction. And in my paper, I have a paper on that that shows they all provide unique variance into predicting mathematics achievement. So there is some overlap there, but that there are also differences between the three representations.
Thanks.
Yeah, I don't know. I'm sorry. I don't know if I answered your question or if we were just, okay.
Yeah.
Good. So if there are any questions, maybe ask Ilyse over the chat, and you can still, communicate with others, and we can go forward in our program. And the next speaker is going to be Katie Gilligan. Thanks again to Ilyse. And we will have Katie on the screen now, who is sharing her screen, and the floor is yours.
Oh. Can you see my screen?
Yes.
Yes, we can.
Yeah. All good.
Okay, excellent. Thank you very much for having me, and thank you, Wenke, for organizing this symposium. Can I just check you're seeing it in full screen and not in the part with the slides on the side?
We see it in full screen, it's fine.
Perfect. So yes, I'm Katie Gilligan-Lee, and I'm an assistant professor at the University of Surrey in the United Kingdom. And today I'm going to present the results of some meta-analysis work that I have been completing with Dr. Zach Hawes from the University of Toronto and Professor Kelly Mix from the University of Maryland. And I think both Zach and Kelly are here today, or virtually here. So if you do have any questions as I'm going through, please stick them into the chat, and hopefully one of them will be able to help you. I think I'm having some slight... Has that moved on to the next slide?
No.
No. Ah, no.
Now.
Excellent, thank you. So the rationale behind this meta-analysis has come from two observations on spatial thinking. So the first one is the idea that spatial skills are malleable, or that they can be changed through intervention. So the best example of this is probably David Utall and his colleagues' meta-analysis from 2013 that found that spatial training led to moderate size gains in spatial skill with an average effect size of Hedges G is 0.47. And the second finding that has prompted this meta-analysis is that which spatial and mathematical thinking show reliable associations with each other across many populations, including children, adolescents, and adults. And it's this piece of research that really brought myself, Kelly, and Zach together to work on this, as this is an area that all three of us have published in and are interested in. And so based on these findings, it has been proposed in the literature that maybe spatial training might give us this extra 2-for-1 effect, in so much as it may lead to benefits in not only spatial skill, but also in maths. And so in the past 5 to 10 years, we've seen this really nice growth in studies that have investigated this very question. And so that is whether or not an intervention in spatial training might lead to extra benefits or transfer of effects to mathematics. However, these studies have differed on a number of different metrics. They've delivered different types of training. They've been based in different populations with different theoretical grounding and methodologies. But overall, the question remains the same, and that is it possible that spatial skills might have this causal effect on mathematical skills? And so the aim of our study was to consolidate the research in this domain and really to determine whether, why, and under what conditions spatial intervention might lead to improvements in maths outcomes. And so the specific research questions that I'm going to talk about today, the first one is, can we replicate the results that David Utall and his colleagues found in 2013 to show that spatial training has an effect on spatial skill? The second question is, do spatial training gains transfer to math outcomes? And the third one is, what are the moderators in this effect? So what different features or conditions of spatial training might be important or affect the size of the gains that are reported? So this meta-analysis was completed in line with the PRISMA guidelines. So alongside doing database searches, we really made an attempt to address the file drawer issue. So we had calls on international mailing lists for unpublished data. We looked at the abstracts from recent conferences, and we looked at the reference lists for the papers that we had included in the meta-analysis. And at the bottom of this screen, you can see an overview of the inclusion criteria that we had for this study. So first of all, the study had to have, or the paper had to have a pre-test, post-test design. And unfortunately, this meant that we lost a few papers who only included measurement of spatial or math skills at post-test. The study had to include a control group. And in cases where there was more than one control group,
we used the control group that most closely matched the experimental group. And so by that I mean, for example, in a study of children with mathematical learning difficulties, we included the control group of children who also had mathematical learning difficulties, as opposed to a typically developing control group. The paper had to include sufficient data for effect sizes to be computed, or in some cases we were able to contact the authors, and if they provided this data, the paper was included. The study had to include at least one maths outcome, and they had to include a spatial training intervention of some description. So each step of the reviewer screening was completed by 2 independent reviewers, and we had a reliability of at least 99% for each of the stages. And in short, what we found were 28 studies that fit our criteria, and these included 89 independent comparisons and included 3,765 participants. And this far exceeded our expectations on what we were going to find in the literature on this research question. And so in this slide, I have provided an extremely brief overview of the analytical strategy. If you are more interested in this, please email us and we can send you more details. But we generated our effect sizes using the comprehensive meta-analysis program. And then all of our subsequent analysis we completed in RStudio. So we used robust variance estimation, which allows us to control for dependencies between effect sizes. And for anyone who's not familiar with meta-analyses, this basically means that for some of our studies that might have included several measures of math skill, this allowed us to include each of these effect sizes and account for the dependency within the study instead of creating an average effect size per study. And so we used the robust variance estimation in Robu meta package, and we'd really like to thank Elizabeth Tipton for her help in us getting this up and running. And finally, to look at the moderator effects, we used regression models, and again, we used the Robu meta package. And so for the first of our results, so on this slide, we can see the overall effect of spatial training on spatial outcomes. And so we can see here that our result very closely resembles that was reported in the Utah paper of Hedges G of 0.52. And what's really nice about this finding is that only 4 of the studies that were included here are also included in the Utah paper. And furthermore, while the majority of the papers that were included in the Utah meta-analysis were based on adults, the majority of the papers included here are based on child or adolescent populations. And so I suppose the take-home message from this slide is just that here we've provided some additional support on the malleability of spatial thinking. And then now I suppose for the moment we've been waiting for, which is whether or not there is an effect of spatial training on maths. And so for this effect, we did find a small to moderate effect of spatial training on math outcomes. And so if you look at the forest plot that we've presented, it's worth me highlighting that here we have included an average effect size for each study. And this means that for several of the studies in the forest plot, they actually included several maths outcome measures. And so the average effect here doesn't obviously show studies that might have had 5 or 6 different outcomes. But we can see for a lot of these studies, we are seeing a positive effect of spatial training on maths. And so the take-home message that we've taken from this is that these results are really quite promising, particularly in relation to classroom practice and how they might help maths learning. And so these are an added bit of evidence that suggests that in fact, integrating spatial thinking into the classroom this suggests will have a positive impact on maths performance. And so the next thing that I'm going to briefly talk about is the role of moderators. And so we looked at several moderators to explore their effects on how they may influence the size of the gains reported. So we looked at approach to training. So this we described as either being pure or embedded. And so pure training was that which involved training in spatial skill only, whereas embedded training was embedded within a math classroom or a math context. We looked at study design, so comparing randomized control trials to quasi-experimental designs. We looked at how the training was delivered. So this is whether it was delivered by a classroom teacher, by a researcher, or whether it was computer-based. We looked at the type of control group. So whether we were looking at a business as usual control group or an active control group. We also looked at the dosage of training, which was a continuous variable. That was the amount of minutes of training that were delivered overall. We looked at the type of math outcome measure, comparing different types of math outcome. The participant age, so whether or not the effects or transfer of training gains from spatial to math skills increases or decreases with age. And finally, we looked at the timing of post-test. So exploring whether we saw larger gains or differences in gains depending on when the post-test was completed relative to the training. And so I have to say that this is the ultimate teaser slide because we are not yet in a position to share the results of our moderator analysis. But we're hoping that this will entice you to keep following the results of our meta-analysis. And we hope that we'll have more results to share on this soon. And I think that that is all we have time for. And I think I have kept under my 10 minutes. So if anyone has any questions, I am more than happy to answer them.
Thank you very much, Katie. That was very interesting, and you're right. I was totally curious about the moderator analysis. But I'm very looking forward to seeing the results. But are there any questions?
I have what might be a kind of bizarre question. I'm curious if you've compared the effect of spatial training on math outcomes to typical effects of math training on math outcomes. And if so, which is bigger?
So we have had a look. So one of our control groups, actually, so we have in our active comparing experimental, so that would be spatial training, to active control groups. Some of those include additional mathematical lessons. And so we do have that in there as a moderator variable. But again, we are not yet ready to say definitively of whether or not it's making a difference. But I will say preliminarily, no, it doesn't seem to be the case that the type of control group makes a difference. So whether or not they're business as usual or whether or not the control group are doing extra math, it doesn't seem to make a difference. But don't hold me to that, please.
Okay, Katie, there is one more question in the chat from Martin Fischer. Did your survey reveal whether it matters if spatial training tasks are 2D or 3D?
Actually, that's not something that we coded the tasks for. I suppose it's something that we might be able to tell and whether or not the tasks delivered are computer-based or not, because quite often those two things fit. But one of the issues that we did find, or considerations when we were coding the studies, was that for a lot of the things we were interested in, all of the studies fell into one criteria or another. And so in lots of cases, there were not enough studies in each of the categories to have a look. But it's definitely something that we can have a look into. And yeah, we can definitely check and see how they could be coded in a 2D or 3D way.
Great. So thank you very much again, Katie. So we are going to go to the next presentation, which is going to be our final presentation from Tobias Kahl from the University of Basel. So feel free to share your screen.
Yes. Hello, everybody. Can you hear me and can you see my presentation? Yes.
We don't see the presentation yet, but we can hear you. That's good.
Okay. Hold on 1 second.
Now.
All right. Perfect.
Good.
Yeah. Thank you for the opportunity to present a current study that we conducted here. I'm Tobias Kahl. I'm a PhD student at the University of Basel, and we conducted a study on bidirectional associations among executive functions, visual spatial skills, and mathematical achievement in primary school students. And I want to present the results of this longitudinal study. So we know that there are several predictors influencing mathematical achievement, and you can distinguish them into, for example, domain-specific abilities, which are, for example, numerosity, ordinality, approximate number system, etc., and the domain general abilities, besides general intelligence, for instance, executive functions and visual spatial skills, who have been shown to play a key role for mathematical achievement. And we know that executive functions, so let's say as a set of control processes, can be distinguished according to the model of Miyake into 3 core components, which are working memory, inhibition, and cognitive flexibility. And there is a lot of studies showing that these core components predict mathematical achievement to a later point of time in different age groups. And I just want to focus here on preschool students, primary school students. There are also studies on adolescents, for instance. Similar to that, visual spatial skills, for example, mental rotation, spatial assembly, spatial scaling, similarly to executive functions, they also predict mathematical achievement in a later point of time when you consider studies on preschool students, primary school students, and other age groups. So far, these studies, and just a simplified illustration here, they looked at each skill on one time point and mathematical achievement on a later time point, and they looked at this longitudinal effect. So also for executive functions, just a few studies who actually looked at both skills simultaneously, which makes a lot of sense, as you can imagine, when you think of visual spatial skills as the ability to retrieve and to transform visual images, this ability requires executive resources. And these study results can suggest a unidirectional association. So with early executive functions and visual spatial skills predicting later mathematical achievement. And which also makes a lot of sense because we have decades of research showing that cognitive ability is a basis for academic achievement. At the same time, there are studies showing that there's also reciprocal relations between cognitive abilities and academic achievement, and that there are bidirectional patterns. So you can think of, for example, of the theory of mutualism, which states that cognitive and academic skills, they develop in tandem. So they interact mutually and they interact beneficially with each other across child development. And when you think of an example, for example, talking about mathematical achievement and working memory, for example, we all know that we need working memory capacities to do mathematical problems. At the same time, you could think of just doing maths automatically trains your working memory, at least some aspects of mathematics. And these bidirectional relations you can use, for example, a cross-like panel model approach, which is, you know that it's possible to test multiple paths and to point out like the unique longitudinal effects of several variables. Again, that's just a really simple illustration. Obviously, it's you can extend it by different time points, etc. And indeed, there are studies, a few studies investigating this bidirectional relations between executive functions and mathematical achievement in preschool students. So, and most of the studies, they found bidirectional relations, saying that executive functions predict changes in mathematical achievement to a later point and vice versa. There's one exception from Fung. And the authors so far, the possible explanation for this bidirectionality was so far that we need executive resources for mathematical operations and complex tasks. At the same time, this training effect doing math, so if children are more exposed to math problems, so they literally do more math, that may enhance children's executive functions. So this is one possible mechanism that they discuss so far. And the other is from a perspective from the psychology of instruction. So as preschool students where these studies took place so far, they're not exposed to formal mathematics so far. So children, and that's one point, maybe children with higher executive functions, they would initiate more engagement with mathematical content. So whether they like can freely choose, they would go for these more complex tasks, maybe. This is one point here. And the same thing could work for visual spatial skills using a CLPM approach. And indeed, there are studies, as we heard today, in the second presentation as well on bidirectional relations between visual spatial skills and math. And for instance, one study, a recent study that investigated these relations in preschool students, they found that visual spatial skills predict changes in mathematical achievement to a later point of time, but not vice versa. At the same time, there's one study showing that there are bidirectional associations between both skills. In primary school students, in the second study from Geert, they didn't account for other strong predictors, for example, SES and or verbal intelligence. So just as a side note here, but yeah, these two studies, I wanted to show you these results. So, and the aims of the study that we conducted were to assess both skills, so both domain general abilities simultaneously, and to see the bidirectional patterns in primary school students, because in Switzerland it's the first time where they're really exposed to formal mathematics in school, and this is obviously here the time where most of the interventions and most of the diagnostics also take place, and that's what we wanted to focus here on. We used for so the participants of our study were 182 children, an average 7 years old. There was a subsample of a standardization sample that we used from the IDS-2. It's the Intelligence and Development Scales 2. And we reassessed 78 students from this subsample 3 years later. And on average 3 years later, but it differed for individual children because that's due to that the period from T1 was bigger than the period of assessment from T2. Yeah, we handled this by doing age standardized values in our analysis to cope with that problem. And here, yeah, it was a standardized assessment in both time points. Here a mathematical achievement, all assessed with the same instrument, the Intelligence and Development Scales. Mathematical achievement test is here is a, was constructed according to the Swiss school curriculum, and there were 3 indicators assessing executive functions, so inhibition, cognitive flexibility, working memory, visual spatial skills, and verbal reasoning as a control variable. Was assessed by 2 other subtests as well. Additionally, on the second time point, we assessed mathematical achievement by using another standardized math test for having different sections in mathematics, like different areas, arithmetical problems, geometry, and word problems. So we wanted to model a latent we wanted to do a latent approach, but we couldn't do that because the indicators of our main variables, they didn't correlate that high enough. And when we tried to retrieve factor scores for a latent approach, they didn't explain substantial portions of variance. So we did a manifest approach. We accounted for verbal reasoning, gender, and SES. And what you can't see here in the model, because I just put it really in a simple way, all variables can correlate to each other. It was a saturated model, so, yeah, you can see on the second time point, the same variables that are assessed with the additional math test. And here we used the FIMUS, or the full information maximum likelihood. And here you can see the stability path from the subtests. So one assembly task, working memory and cognitive flexibility, and as well the mathematical achievement test. And I just put the paths that are important for our research questions. So an assembly task could predict changes in mathematical achievement 3 years later. And mathematical achievement predicted changes in working memory 3 years later. There was none other, regarding to our research question, other path significant. So discussions, yeah, we counted for these variables, what I already mentioned. What we didn't expect is that EF did not predict changes in mathematical achievement. So this is in contrast with former studies. And with one exception with Fung, and the limitations of the study obviously are, well, we couldn't reliably do a latent approach by modeling the variables in a latent way. And the second one is that we had only 2 time points of measurement, and this is, well, we couldn't disentangle the within and between person effects. So, and a rather small sample size. So, yeah, thank you for your attention. And I'm happy for comments or questions.
Thank you, Tobias. So now it's 4 o'clock. We're actually at the end of the symposium, but we, of course, Andrew wrote us that we could go beyond the time, the allotted time. So are there any questions for Tobias? You can either ask directly or let me know in the chat. And there is, okay, Tyler, thank you so much. He said, great symposium. Thank you to the organizers and speakers. And I would like to also express my gratitude to the speakers. But are there any questions? I don't think so. But if you have some, feel free to email us. Oh, there are questions. Hold on. Katie, do you have any theories as to why spatial assembly might predict math?
Any theories why spatial assembly predict maths? I mean, it could be. Oh, sorry.
No, sorry, it's all right. I was going to say, I think my question is very similar to Zach's. He may have just phrased it more nicely than I did. So you might work together.
Sorry.
I think there is another one, Tobias, from Zach, going into the same direction. It's about the spatial assembly task.
But I mean,
why?
Yes. Okay, I can see that question. So the difference between executive functions and spatial skills, or at least in its mechanisms to mathematical achievement, that's the question as I understand it, right? So, I mean, executive functions, obviously, they are, as I mentioned, like in the very beginning, they are obviously related to to other cognitive abilities, and they maybe are like a more general thing that always plays or comes into play with a lot of different academic achievement tasks, but also other cognitive skills. And I think this is, maybe it's a little bit broader than spatial skills. This is, I think, one point that I would like to add here. And spatial skills, I mean, there are discussions in the literature that they say, okay, is there any need, for example, is it helpful by spatial assembly, for example, to have a spatial imagination that helps in general for mathematics, that we can imagine or visualize mathematical problems in another way, or that we use, for example, other skills that, as we heard before, the mental number line or something like that, and it's generally helpful to put mathematical problems in another way, in a more visualized way. I think these maybe is one general point, and a specific point, obviously, maybe visual spatial skills helps in geometry, for example. I mean, there are also specific mathematical tasks which are directly related to visual spatial skills. This answers your question, I'm not sure.
Okay. I guess. Yes. Katie has asked another question. Did you have other spatial skills that were?
I know we just had assembly tasks here. And one, as you saw in the model, we had two assembly tasks that was slightly different. The one that was a predictor was similar to the block test and the whisk, maybe, for example. So this is more, but no, we didn't have other visual spatial skills. Would be really interesting, because studies showing also, for example, that mental rotation tasks or something like that are often used. Yeah, we didn't have this opportunity.
Great. Katie says thanks, and I think there is no other question. And of course, everyone who would like to discuss with the presenters can stay tuned. And for the rest, the symposium is coming to an end right now. I would like to express my gratitude to the speakers. You really did a great job. And I also would like to say thanks to MCLS, Andrew, the trainee board, for, you know, providing this possibility that we can, exchange our thoughts. Yeah, even Kelly, thanks everyone, great set of talks. I agree. So, all right. So thank you very much. And I already have the next Zoom meeting right now. So I have to leave already, but thank you so much for listening, for asking, for exchanging our work.
Thank you, everyone. We'll see you next week for our next meeting.
Yeah, bye.
Thanks, bye.
Bye.